Now we move to polysaccharides. We have seen polysaccharides are saccharides which on hydrolysis will give you large number of monosaccharides. So in the section of polysaccharide, first we have to see starch. Starch is a polysaccharide of glucose. Glucose molecule combine together to form the macromolecule starch. During the formation of starch molecule, starch consists of two components. They are amylose and amylopectin. So, starch is a colorless polysaccharide which is found in plants, and the monomers is glucose, and it consists of two components or two types of polysaccharide chains. They are amylose and amylopectin. So when we identify the structure of starch, starch is composed of monomer unit glucose which combines together to form amylose and amylopectin. Amylose and amylopectin are present side by side and interdispersed in starch granules. They have unique chemical and physical properties, and their relative properties influence the overall properties of starch. Amylose and amylopectin have unique properties. They have specialized properties, and these properties combined together join show the properties of starch. So we have to see what is the difference between amylose and amylopectin now. So in brief, we could say starch is made up of two components, amylose and amylopectin. Amylose is a polymer of glucose molecule, and amylopectin is also a polymer of glucose molecule. But starch is formed by the combination of amylose and amylopectin. Okay. Now we have to see the difference between amylose and amylopectin, which are the components present in starch. Very, very important. So we have to see what are the properties and difference of amylose and amylopectin. See here, amylose is a straight chain polymer of D-glucose units, while amylopectin is a branched chain polymer of glucose units. So the first difference itself shows that amylose is a straight chain polysaccharide, while amylopectin present in a branched form in starch. The second is amylose constitute 20% of starch, 20% of starch, while amylopectin constitute 80% of the starch. So when we take starch molecule, 20% is amylose while 80% is amylopectin. The third difference is that amylose is less soluble in water while amylopectin is soluble in water. That is why amylose and amylopectin combine to form starch, and starch is partially soluble in water, or starch forms a colloidal solution. So amylose is completely water soluble. It is only 20%, while amylopectin is water insoluble with 80% of its constituents. Then amylose gives a blue color with iodine. That is why we are using amylose in the starch in the titration. Starch is used as an indicator in titrations, iodometry, idimetry titrations, and the blue color of starch is due to the presence of amylose, while amylopectin gives a reddish brown color with iodine. Reddish brown color with iodine. Then amylose is a straight chain polymer which are connected or joined by alpha 1,4 glycosidic linkages. One glucose molecule is connected with another glucose molecule through 1,4 glycosidic linkages. That means the first carbon atom of first molecule of glucose connect with the fourth carbon atom of second molecule of glucose, that is amylose. While in amylopectin, two linkages are possible, that is a 1,4 linkage as well as a 1,6 linkage possible. That means C1 of one glucose molecule combined with the fourth carbon atom of another glucose molecule and sixth carbon atom of another molecule. That is why it forms a branched chain polysaccharide. The molecular weight of amylose is between 10,000 to 50,000, while the molecular weight of amylopectin is to 50,000 to 1 million. These are the main difference between amylose and amylopectin. Very, very important. So, in brief, we could say amylose is a straight chain polymer which is having 20% of starch, which is water soluble, and it gives blue color with iodine, and one glucose unit is connected with another glucose unit through alpha 1,4 linkages or glycosidic linkages, and the molecular mass is 10,000 to 50,000. While for amylopectin, amylopectin is a branched polymer. It constitutes 80% of the starch and it is highly soluble in water and it is a branched structure. Amylopectin gives reddish brown color with iodine. It is having 1,4 and 1,6 glycosidic linkages and the molecular weight ranges from 50,000 to 1 million. Take down. Now see here, we have to see how amylose and amylopectin are bonded to form from glucose molecule. We know for amylose and amylopectin, the monomer is glucose unit. And how the linkages is going on in amylose and amylopectin. See here, this is amylose. And this is the first carbon atom of alpha D glucose. And this is the fourth carbon atom of another alpha D glucose. So, the first carbon atom of the first glucose molecule combined with the fourth carbon atom of second glucose molecule. And again, the first carbon atom of second glucose molecule combined with the fourth carbon atom of another molecule. And it continues to form a straight chain amylose molecule. So, the alpha carbon atom, or we can say the anomeric carbon atom of alpha D glucose, which is having first position of the carbon atom, which combines the fourth carbon atom of second molecule of glucose unit. This will continue. That means 1, 4, 1, 4, 1, 4. This is the glycosidic linkages to form straight chain amylose molecule. But in amylopectin, this happens. That is 1,4 linkages happens. First carbon atom with the fourth carbon atom. So the OH group of first carbon atom and the OH group of fourth carbon atom undergoes linkages. But after some time, we see here the first carbon atom is bonding with the sixth carbon atom, that is the CH2OH group of another strand of glycosidic linkages. That means in amylopectin, 1,4 linkages are there and there are also 1,6 linkages. So this is a straight chain molecule. Coming here, the first carbon atom combines with the sixth carbon atom of another chain. So a branch has come. This will continue, again it happens. So in amylopectin, alpha 1,6 glycosidic linkages are there and there is also alpha 1,4 glycosidic linkages. Take down the structure. Structure is not important, but you should identify what is alpha 1,4 glycosidic linkages and how amylopectin is a branched compound while amylo is a straight chain compound. Take down. Now we move to another polysaccharide, that is cellulose. Cellulose is basically a polysaccharide of glucose unit, or we could say glucose combined together to form cellulose molecule. And cellulose molecule is a straight chain compound. It is found in the cell walls of plants. And the most important thing is that cellulose is a non-reducing sugar like starch because it does not have a free aldehyde group. See here, it is a polysaccharide. It is formed by the linkage of glucose units. It does not have a free aldehyde group. It is not a reducing sugar and it is found mainly in plants. In cellulose, the glucose units are beta D glucose units. In starch, we have seen it is alpha D glucose units. But in cellulose, it is beta D glucose units. The linkage is same. In amylose, we have seen the linkages is alpha 1,4 linkages. That is the linkages between the C1 carbon atom and the C4 carbon atom. C1 and C4 carbon atom. Same linkage is present in cellulose, but the monomer is beta D glucose units. That means the structure of amylose and cellulose is same except that in amylose it is alpha D glucose units connected while in cellulose it is beta D glucose units are connected. For both amylose and cellulose the linkage is C1 carbon atom, that is the OH group of the C1 carbon atom of one glucose molecule of beta D glucose with the C4 carbon atom of another molecule of glucose unit. So in cellulose it is beta D glucose units. Very, very important. Take down. Now see here how cellulose is formed from beta D glucose. See here, this is a beta D glucose molecule. This is another beta D glucose molecule. This is the anomeric carbon atom with OH group on the top place. That is beta. Here this is also a beta D glucose. Now see here this OH group, that is the one position C1 position, first carbon atom, combined with the fourth OH group. See, this is C1, C2, C3, C4. fourth OH group to form a linkage here. So first combines with the fourth, that means first OH group of one molecule combines with the fourth OH group of another molecule to form a 1,4 linkage. Now see here, for this molecule, this is the fourth position, and its first molecule again combines with the fourth position of another molecule. Again, the first OH group, the OH group on the first carbon atom, that is the anomeric carbon atom, combines with the fourth OH group. This will continue to form cellulose molecule. So in cellulose, it is beta D glucose units are connected by 1,4 alpha glycosidic linkage. So in alpha D glucose, sorry, in starch, it is alpha D glucose, while in cellulose, it is beta D glucose undergoing 1,4 glycosidic linkages. Take down. See here, this is the linkage 1 OH group, that is the beta, combined with 4 OH group. H2O is eliminated. H2O is eliminated, and an oxygen linkage is formed. Oxygen linkage is formed. Again, see, first OH group of this molecule combined with the 4 OH group of another molecule. H2O is eliminated, and oxygen linkage is formed. This is the formation of cellulose from glucose molecule. Is it clear? Take down. These are the industrial applications, important applications of cellulose. Cellulose composed of 87 to 90% of cotton fibers. Many medicines are derived from plant cellulose and cellulose acetate. And cellophane is a viscous cellulose reaction with sulfuric acid. So sulfuric acid react with viscous cellulose and the product is cellophane, and it is used as explosive, as bomb materials. Cellulose trinitrate is a powerful blasting material. Then it is used in energy drinks and in many industrial purpose. So the application of cellulose are immense. So again, these are the applications of cellulose. Cellulose used in manufacture of cotton and linen materials, which are used as dress materials. Then cellulose trinitrate is an effective explosive called gum cotton. It is not gum, it is gun cotton. Then many synthetic plastic materials are manufactured by mixing celluloids with different polymers, and even cellulose is used as materials for artificial silk. These are the important applications of cellulose. So take down.